Integration using trigonometric identities and shifts. Okay, so let's begin with this new section on integration. Now, recall what we've covered so far. In previous sections, we've been looking at techniques for simplifying integrals, and a key one we've practiced is substitution, finding a simpler function to substitute into the integral to make it more manageable. This slide introduces a slightly more nuanced situation. Sometimes, we encounter integrals where the argument of a trigonometric function isn't just x, but something like x plus a constant, where a represents a constant value. For example, we might see sine of x plus a. This x plus a is what we call a shifted argument. Think of it as the trigonometric function being slightly moved or phase shifted along the x-axis. Now, these shifts can make the integral appear more complicated, especially when you have a situation where the numerator and denominator of your integrand, the function you're integrating, have different arguments. For instance, you might have sine of x in the numerator and sine of x plus a in the denominator. That difference in arguments is what creates the difficulty. Therefore, the main goal of this subsection, and what we'll be focusing on, is to synchronize these arguments. What I mean by that is, we want to manipulate the integral, usually through substitution, so that the arguments of all the trigonometric functions are the same. Once we achieve that, we can then apply the standard integration formulas we already know. So, the core idea is to simplify by aligning those arguments before we integrate. We'll be building on our substitution skills, but with this added layer of dealing with shifted trigonometric functions. In the following slides, we'll break down exactly how to do this step by step. Understanding the concept. So, the first point here states that a shift in trigonometry is also known as a phase shift. Think of it as a horizontal slide of a trigonometric wave. Next, it connects this idea to real-world applications. Phase shifts aren't just abstract mathematical concepts, they appear in fields like electronics and acoustics. Imagine two sound waves. If they aren't perfectly in sync or aligned in time, that difference in alignment is a phase shift. It's like one wave is leading or lagging behind the other. Mathematically, we represent this phase shift by adding a constant to the angle of a trigonometric function. For example, it says sine of x plus a, that would be pronounced as sine of x plus a. The a represents the amount of the shift. So, instead of a simple sine wave starting at 0, this wave starts at a different point on the y-axis. Now, here, s where it becomes important for integration. The slide points out that if you have an integral with, say, sine of x and sine of x plus a, you can't directly integrate that combination. The standard integration formulas for sine just won't work when the arguments, the expressions inside the sine function, are different. Therefore, the slide concludes by outlining our strategy. We need to use a substitution technique to make those arguments identical. Once we've done that, we can then use trigonometric identities, which we'll review shortly, to expand the expression into a form that is integrable. Remember, the goal is to manipulate the integral into a form we know how to solve. We'll be looking at how to do this step by step on the next few slides, starting with identifying that shift and performing the substitution. Okay, let's move on to slide 2. As we discussed on the previous slide, some integrals can be tricky because of shifted arguments within the trigonometric functions. This slide helps us understand what that shift actually means and why it causes problems for direct integration. Step-by-step methodology. Okay, so let's move on to a systematic approach to tackling these integrals with shifted trigonometric functions. This slide, titled Step-by-Step Methodology, outlines exactly how we're going to do it. Remember from the previous slides, we've established that these shifts, like having both sine of x and sine of x plus, make direct integration tricky. We need to align those arguments. 1. Identify the shift. The very first thing we do is pinpoint where the shift is happening. We're looking for a term within the trigonometric function where the argument of x is altered by a constant. For example, if you see something like x plus a, that plus a indicates a shift, and that's what we need to focus on. 2. Perform substitution. This is where we introduce a new variable to simplify things. we let the shifted argument, that is, x plus a, be equal to a new variable, which we'll call t. So, t equals x plus a now. This might seem like adding more complexity, but it's a crucial step. Because t equals x plus a, we can rearrange this to solve for x in terms of t. That gives us x equals t minus a. Importantly, when we do this substitution, the differential dx also changes. Since we've expressed x in terms of t, dx becomes simply dt. Remember this, dx equals dt, it's vital for the integration process. 3. Rewrite the integral. Now we take our original integral and replace everything in terms of t. We substitute t minus a for x and dt for dx. This substitution is designed to simplify the denominator, often turning it into a simple trigonometric function like sine of t. The numerator will then contain a trigonometric function with the shifted argument, like sine of t minus a. 4. Apply trigonometric identities. Once we've made the substitution, we often have a trigonometric function of a difference within the numerator. This is where our trigonometric identities come into play. Specifically, we'll use the angle subtraction formulas for sine and cosine. Let's recall those. Sine of a minus b is equal to sine of a times cosine of b minus cosine of a times sine of b, and cosine of a minus b is equal to cosine of a times cosine of b plus sine of a times sine of b. We'll use these to expand the numerator, breaking it down into individual terms. 5. Split the integral. After expanding the numerator using the trigonometric identity, we'll have a sum or difference of terms. We can then split our single integral into multiple simpler integrals, one for each of those terms. This is based on the property that the integral of a sum is the sum of the integrals. 6. Integrate and back substitute. Finally, we integrate each of these simpler integrals. Remember that any constant coefficients will simply come along for the ride. Once we've integrated, we need to substitute back to express our answer in terms of the original variable, x. That means replacing t with x plus a. And don't forget to add the constant of integration, c, at the end. So that's the complete process. It might seem like a lot of steps, but each one is designed to simplify the integral and make it solvable. We'll see this in action on the next few slides with a detailed example. Detailed example. Okay, let's tackle this integral together. As we discussed in the previous slides, we're dealing with an integral where we have a shift in the trigonometric argument. This slide presents our specific problem and begins the solution process. Here's the integral we need to evaluate. It's the integral of sine x over sine of x plus a with respect to x. Now, the first step, as outlined in our methodology, is to identify the shift. Looking at the integral, we can clearly see that the argument inside the sine function in the denominator, x plus a, is shifted compared to the sine x in the numerator. To simplify things, we're going to perform a substitution. We'll let t equal x plus a. This is a key step because it will allow us to rewrite the integral in terms of t, making it easier to handle. If t equals x plus a, then we can solve for x in terms of t. Subtracting a from both sides gives us x equals t minus a. And importantly, when we perform this substitution, we also need to consider the differential dx. Since x is now expressed as t minus, the differential dx becomes dt. Remember from calculus that if y is a function of x, then di equals the derivative of y with respect to x, multiplied by dx. In our case, since dx is the differential of x, and x is now t minus a, dx is simply equal to dt. So we've now completed the substitution step. We've identified the shift, defined our new variable t, expressed x and dx in terms of t, and are now ready to move on to rewriting the integral using this substitution, which we'll do on the next slide. Detailed example continued. Now in step 2, rewrite the integral. We're actually doing the substitution. Remember we let t equal x plus a, and consequently, x became t minus a, and dx simply became dt. So when we substitute those values into our original integral, we get the integral of sine of t minus a all divided by sine of t with respect to dt. I'll say that again mathematically. The integral from t to dt of sine of t minus a over sine of t. See how the shifted argument, x plus a, is now neatly represented as t minus a? This is exactly what we wanted to get everything in terms of t. Now let's move on to step 3. Expand using trigonometric identity. Notice that we have sine of t minus a in the numerator. This is where our trigonometric identities come into play. Specifically, we're going to use the subtraction formula for sine, which states that sine of a minus b is equal to sine of a times cosine of b minus cosine of a times sine of b. Applying this to our numerator, sine of t minus a expands to sine of t multiplied by cosine of a minus cosine of t multiplied by sine of a. Therefore, our integral now becomes the integral from t to dt of the quantity, sine of t times cosine of a minus cosine of t times sine of a, all divided by sine of t. This expansion is crucial because it allows us to split the fraction in the next step, making the integral much easier to handle. We've successfully transformed a potentially complicated integral into a form where we can apply simpler integration techniques. Remember, the goal is always to manipulate the integral into a manageable form, and this expansion is a key step in achieving that. Okay, let's move on to slide 5. As you recall from the previous slides, we were tackling the integral of sine x over sine of x plus a, and we began a substitution to simplify things. Detailed example continued. Okay, let's move on to slide 6. As you recall from the previous slides, we were working on evaluating the integral of sine x divided by sine of x plus a, and we've already performed the substitution, replacing x plus a with t, and x with t minus a. This led us to the integral of sine of t minus a divided by sine of t with respect to t. Now, looking at this slide, step 4, split the fraction. We have the integral of, and I'll read this out carefully, sine of t multiplied by cosine of a minus cosine of t multiplied by sine of a, all divided by sine of t. With respect to t, what we're doing here is simply applying the distributive property of division over addition and subtraction. We're breaking up that single fraction into 2 separate fractions. So, we have the integral of sine t cosine a over sine t, minus the integral of cosine t sine a over sine t. Remember, this is perfectly valid as long as sine t is not 0, which we'll assume for the sake of this problem. Now, let's move on to step 5. Simplify the terms. If you look at the first integral, sine t in the numerator and denominator cancel each other out, leaving us with just cosine a. The second integral simplifies beautifully as well. Remember from your trigonometric identities that cosine t divided by sine t is equal to cotangent t. Therefore, our integral now becomes the integral of cosine a minus sine a multiplied by cotangent t. With respect to t, so, we have simplified the integral to a form where we can now easily integrate each term separately. In the next slide, we'll actually perform that integration and then, importantly, remember to back substitute to get our final answer in terms of x. Does that make sense so far? Detailed example continued. Now remember that a is a constant. This is crucial, because a is a constant. Trigonometric functions of a, like cosine a and sine a, are also constants. When we integrate, we treat them as coefficients multiplying the integral. So we have the integral of 1 with respect to t, which is simply t multiplied by cosine a. That gives us cosine a times. Then we have minus sine a multiplied by the integral of cotangent t with respect to t. Recall that the integral of cotangent t is the natural logarithm of the absolute value of sine t. So that part becomes minus sine a times the natural logarithm of the absolute value of sine t plus our constant of integration, which we denote as c. Therefore, our integral I at this stage is equal to t times cosine a minus sine a times the natural logarithm of the absolute value of sine t plus c. Now this is a step students often miss. We need to express our answer in terms of our original variable, which was x, not t. Remember our substitution? We define t as x plus a. So, we simply replace every instance of t in our integrated expression with x plus a. This gives us x plus a multiplied by cosine a minus sine a multiplied by the natural logarithm of the absolute value of sine of x plus a plus c. And there you have it. This is our final answer. we've successfully evaluated the integral using trigonometric identities, substitution, and careful back substitution. In the next slide, we'll quickly review some common mistakes to avoid when tackling these types of problems, so pay close attention to those to ensure you don't fall into those traps. Okay, let's move on to the final steps of evaluating this integral. As we've established, we've successfully used substitution and trigonometric identities to get to a point where integration is straightforward. Common mistakes to avoid. Okay, let's move on to slide 8. This slide highlights some common pitfalls students encounter when tackling these types of integration problems, so pay close attention. 1. Treating constants as variables. A very frequent mistake is to treat the constant a as if it were the variable x. Remember, a is just a number. So when you integrate something like cosine of a with respect to t, you treat cosine a as a constant coefficient. This means the integral of cosine a with respect to t is simply t times cosine a, not sine a. It's easy to fall into the trap of applying the integration rules for x to constants, so be mindful of that. 2. Incorrect identity application. Next, be extremely careful when applying the trigonometric identities, specifically the subtraction formula for sine. Recall that sine of a minus b is equal to sine a times cosine b minus cosine a times sine b. It's crucial to remember the minus sign. A lot of students mistakenly write a plus sign instead, which will completely change your answer and lead you down the wrong path. Double-check that you've written the formula correctly before expanding. 3. Forgetting back substitution. This is a simple but surprisingly common error. After you've performed the substitution and integrated with respect to t, you must substitute back to express your final answer in terms of the original variable, x. We initially defined t as x plus a, so remember to replace every instance of t with x plus a before you finalize your answer. Leaving your answer in terms of t means you haven't fully completed the problem. 4. Ignoring the absolute value in logarithms. Finally, when integrating cotangent t, you'll arrive at a natural logarithm. The correct form of the integral of cotangent t is the natural log of the absolute value of sine t, written as log absolute value sine t. The absolute value is essential because the logarithm is only defined for positive arguments. Omitting the absolute value makes your answer mathematically imprecise, and you could lose marks on an exam for that. So, keep these 4 points in mind as you practice these types of integrals. They're all easily avoidable mistakes, but they can significantly impact your final result. Now, let's move on to the final slide where we'll summarize the key takeaways from this section. Key takeaways. Okay, let's recap everything we've covered regarding integration with trigonometric identities and shifts. This slide summarizes the key takeaways, so pay close attention. It's a good checklist to run through when you encounter these types of problems. First point, goal. The objective is to make the arguments of the trigonometric functions consistent. Now, remember from the beginning, these shifted arguments, like seeing both sin x and sin of x plus a in the same integral, create difficulty. Our main aim with the substitution technique is to get those arguments to match up. We want to rewrite the integral, so we're dealing with trigonometric functions of the same angle, making it easier to apply standard integration rules. Next, substitution strategy. Substitute the shifted argument, for example, t equals x plus a, to simplify the denominator. As we saw in our detailed example, identifying that shifted argument is the first step. Then, by letting t equal x plus, we effectively remove the shift from the denominator, making it a simpler trigonometric function like sin t. Don't forget that this also means we need to express dx in terms of dt, which in this case is simply dx equals dt. Moving on, identity usage. The subtraction formulas for sine and cosine are essential tools for expanding the numerator after substitution. Once we've made the substitution, we often end up with a numerator that still contains a difference of trigonometric functions. That's where our trigonometric identities come in. Specifically, the sine of a difference, sine of a minus b, and the cosine of a difference, cosine of a minus b, are crucial for breaking down that numerator into terms we can integrate. Remember those formulas. Sine of a minus b is sine a cosine b minus cosine a sine b, and cosine of a minus b is cosine a cosine b plus sine a sine b. Finally, linearity. Once the integral is split, treat the trigonometric functions of the constant, a, as coefficients, that is, constants. After applying the trigonometric identity and splitting the integral into separate terms, remember that cosine a and sine a are just constants. They don't depend on our variable of integration, t or x. This means when we integrate, we can simply pull them out of the integral as constant multipliers. So the integral of cosine a with respect to t is just t times cosine a, and so on. Keep these 4 points in mind, and you'll be well equipped to tackle integrals involving trigonometric functions with shifted arguments. We've built up a solid methodology, and now it's all about practice to solidify your understanding.